In this short video, I'll be discussing the empirical formula and how to find it based on the percent composition of a substance. So the first thing we have to know is what the empirical formula of a substance is, because that's new vocabulary to us. So generally speaking, you can think of the empirical formula of a substance as the formula of a substance in lowest terms. Okay, the molecular formula, however, is the actual formula of the substance. So that is the actual formula. All right, so some substances, they have an empirical formula that's the same as their molecular formula. Some of them are different. For instance, if you have benzene, benzene has a molecular formula of C6H6. That's its actual formula. However, if you wrote out its empirical formula, you'd reduce that down to lowest terms, which would just be something like CH. All right, if you're looking at something, though, like carbon dioxide, which is CO2, that's already in its lowest terms. So CO2 is the molecular formula for carbon dioxide. It is also the empirical formula. In this next section, what we're supposed to do is classify things as either empirical formulas or molecular formulas. The assumption here is that if it's in its lowest terms, we're going to call it an empirical formula. However, if it's not in lowest terms, it's necessarily a molecular formula. So CH4, to start off with, that is in lowest terms, so it is an empirical formula. H2O, also in lowest terms, so that is an empirical formula. C6H8, that one is a molecular formula. All right, if you reduced it down, you would get an empirical formula equal to C3H4. C3H4. All right, for C3H4, that one is empirical already. And then for PO3, that one is empirical. N2H4 is a molecular formula, and the empirical formula, if we were to reduce that down, would be just NH2. And then NO2 is just an empirical formula already. All right, so that's how that one works. So now I'm going to go through the process of calculating something's empirical formula by looking at its percent composition. So to start off here, we have a series of 4 different steps. All right, and so the first thing I kind of do is I start by making a table here. I just write lines over each of the substances and the percent composition to make cells of a table, and then I write it down here. And the first thing that we do is we assume that we're going to have 100 grams of the stuff. All right, and if we've got 100 grams, for instance, and 40% of it is carbon, then we're going to have 40 grams of carbon. All right, and then if we've got 53.33% oxygen, then it's going to be 53.33 grams of oxygen. And so the idea here is if you just assume 100 grams, then 40% is 40 grams, and 53.33% is 53.33 grams, and then for hydrogen we have 6.67 grams of that. All right, and it adds up to be 100% or 100 grams altogether. The next thing that we do is we have to go from mass to moles. All right, this is step number 2. Now, in order to do that, what you have to do is you have to divide by the molar mass, and this is important that you understand how to do each of these steps, because it's basically the same process over and over again. Sorry, divide by the molar mass. Okay, so carbon's molar mass is 12.01. If you divide 40 by 12.01, you get 3.33. Oxygen's molar mass is 16.00. If you divide 53.33 by 16.00, you get 3.33. 6.3, and then lastly 6.67 is the mass of hydrogen. Divide that by 1.01, which is the molar mass for hydrogen from the periodic table, and you get 6.60. All right. So again, to get the moles column, you just take the mass that's listed there, copied over from the percent composition, and then you divide that by the molar mass, which comes from the periodic table. The next thing we need to do is figure out what ratio exists between these different number of moles. To do that, you divide by the smallest number of moles. And so we've got 3.33, 3.33, and 6.60. The smallest number there is 3.33. All right, so we divide each of these by 3.33. 3.33 divided by 3.33 is 1. All right, and then the second one, 3.33 divided by 3.33 is 1. And then 6.60 divided by 3.33, we get 1.98. All right, so that is the general ratio there. Okay, what we need to do in the end, and this step will make more sense here in a minute, but we have to get these to be whole numbers. All right, and so whole numbers is the next column that we do here. These ones, if you look at them, it looks actually like we're right around some whole numbers right now. We've got 1, 1, and 1.98 is about 2. All right, so as whole numbers, we would write them that way. As I said, I'll give you an example in a minute here of when the numbers and the ratios aren't quite so nice, and then we have to do some multiplication to get the whole numbers. And so this one, that last step of going from the ratio to the whole numbers was really easy. It was just copying over, but sometimes it's a little bit more difficult. So the last step here, we've got, for our ratios here, we've got, or our whole number ratios, we've got 1 carbon, 1 oxygen, 2 hydrogens. And so the formula here, 1 carbon, 1 oxygen, 2 hydrogens is COH2. And the whole point of it is to find this empirical formula in the end. I'm going to do one more example down here with problem number 2 actually on the homework, and then I will do another example from the back. So again, the way that we started this off is I just draw lines above each of these percent compositions. All right, and then down to make the cells. So we start off with mass. All right, remember the way that you get the mass is you just assume that we've got 100 grams and then copy the percentages over. So 57.5 grams and 40.0 grams and then 2.50 grams. The next thing we're going to do is divide by the molar mass. For sodium, the molar mass is 22.99. All right, so we divide 57.5 by 22.99, and you get 2.50. This is to get moles, by the way, because that's the next step. So we're dividing by the molar mass of the element from the periodic table. All right, so then we're going to take oxygen and divide it by its mass on the periodic table. The mass of oxygen is 16, so 40 divided by 16 is 2.50. All right, and then the last one, we've got hydrogen there. We're going to divide it by 1.01. All right, 2.50 divided by 1.01 is 2.48. Okay, then the next step is finding the ratio. Again, as a reminder here, what we do is we look at the number of moles and we find the smallest one. So we've got 2.5, 2.5, and 2.48. The smallest one there is 2.48. So we divide all of these by 2.48. You get kind of an automatic number 1 there because 2.48 divided by 2.48 is 1. All right, then for the other ones, we do 2.50 divided by 2.48, and you get 1.01. And then again, 2.50 divided by 2.48, and you get 1.01. All right, and then this one, again, is one where it seems like we have nice whole numbers already. So the whole numbers it looks like we're dealing with here is 1, 1, and 1. And so this formula is called Na, 1 sodium, 1 oxygen, 1 hydrogen. That is sodium hydroxide that we are dealing with. All right, now I'm going to go through that example with you where the numbers aren't quite so nice. It's actually going to be the last problem on this worksheet. Number 6. Same general strategy. First step, copy the percent compositions over as masses. So that's 37.0 grams. And next one, 2.20 grams. Oxygen, 42.3 grams. And then nitrogen, 18.5 grams. Okay, so first step's pretty easy. The second step, we need to get to moles. The way you do that is by dividing by the molar mass for each element. All right, molar mass of carbon from the periodic table is 12.01. So we do 37 divided by 12.01, and you get 3.08. All right, then for hydrogen, we do 2.20 divided by 1.01, and you get 2.18. All right, then for oxygen, you do 42.3 divided by 16.00, and you get 2.64. All right, and lastly, for nitrogen, you do 18.5 divided by its molar mass, which is 14.01, and you get 1.32 as the number of moles there. Next step, we've got to get ratios. You do this by dividing by the smallest. So if you look at the number of moles there and you find the smallest, 1.32 is the smallest. So we're going to take all of these numbers of moles and divide them by 1.32. So that one is a 1, because 1.32 divided by 1.32 is 1. All right, then starting up here at the top, 3.08 divided by 1.32, you get 2.33. And then 2.18 divided by 1.32, you get 1.65. All right, and then 2.64 divided by 1.32, you get 2. So all of those just dividing by the smallest number of moles there to get the ratio. Now you'll see here, these ratios are actually not nice and near whole numbers. We get this weird 2.33 and 1.65. And you have to kind of think about what fraction they're near. All right, so 2.33, hopefully if you're good at math or thinking about the way the fractions are, 2.33 looks a lot like 2 1/3. All right, and 1.65 is pretty close to 1 2/3. All right, and so what we're dealing with here is some ratios that are in thirds. If we want to get these to whole numbers then, what we have to do is we have to multiply by 3. All right, so we multiply all of the ratios by 3 in an attempt to get them to whole numbers. So 2 1/3 times 3 ends up giving you 7. 1.65 is at roughly 1 2/3 times 3 ends up giving us 5. All right, 2 times 3 just gives us 6, and 1 times 3 is 3. All right, so we multiplied all those by 3 to get rid of those fractional decimals there. That 0.33 is about 1/3, 0.65 is about 2/3, and so we multiplied them all by 3 to get into whole numbers. And so the formula for this then is C7, H5, O6, N3. Okay, so that is the general process for finding the empirical formula. I'm not going to do the rest here because it's the same process repeated over and over again, but make sure that you check and see that you're getting these right. A PDF version of the key will be posted online. And also, look in the future, there will be questions on the review and questions on the practice exam, and just make sure that you, generally speaking, understand this process.